Okay, are there any questions on this? Joseph? Well, so 6H plus came from here. So from the half reaction from table 19.1, this was the reaction from the table, but we had to multiply this one by 3 because we wanted to make sure the same number of electrons gained by the H2O2 is equal to the same number of electrons lost by the gold.
So like as far as like when the reaction happens, it's just like already in the air or something, or
yeah. So when this reaction occurs, that means that you need 3 moles of H2O2 reacting with 2 moles of gold for the oxidation reduction reaction to occur. Okay. Now in your previous chemistry class, not in Chem 1A, but in either Chem 22 or high school, did you learn how to balance the oxidation reduction reaction? Yeah. Okay, we're going to review this, how to balance an oxidation reduction reaction, but let me tell you that really, if the half reaction is in table 19.1, there's no real reason to learn how to do that, except if that reaction isn't in table 19.1. Okay. So a lot of reactions are either in, now this is not a very extensive table. There are actually more extensive tables of the standard reduction potentials. Okay, so really, like I'm saying, rather than learning all those rules which you learned in your high school chemistry or Chem 22, really you can look up the half reactions for the reduction and then for the oxidation in table 19.1 and just combine them together to get your overall oxidation reduction reaction. Okay? So I read some quote from Einstein. Someone asked Einstein, how many feet are in a mile? And he goes, I don't know, I don't care. I can just look it up in a reference book in a minute, so why should I clutter my brain with stuff like that? So, same thing here. There's enough rules to remember how to do things, so if you need to find something, just look it up in this table. Okay, so we'll do one reaction. We'll balance one oxidation reduction reaction just to say that we did it in Chem 1B. Then we're not going to do any more of those. We'll just look it up in the table 19.1. Okay, so we'll do it. And I'm not going to ask you to balance a oxidation reduction reaction on an exam or a quiz, because if I do, you can just look it up in table 19.1. So let's do question 19.2c. And that's on page 695 in the textbook. And actually, maybe let's do it on this side here. Okay, so we'll keep table 19.1 on that side of the chalkboard. Because really, see, when you were looking for a job after you get your bachelor's degree, or if you get a higher degree, you're looking for a job. I mean, some interviewers are going to ask you, balance this oxidation reduction reaction using the method of half reactions. You'll never get asked that question. Then, or if you're trying to balance, let's say you're working in some job and at some, say, steel plant, you want to figure out, okay, there's some reaction going on. It must be an oxidation reduction reaction. So they're not going to. Your boss is going to tell you, oh, this must be iron, and this must be rust. So let's use this method of half reactions to balance. You never do that. You just look it up. Okay, so really, it's no. Although you learn all the things. I mean, if there's a reference to use, just use the reference. Okay, so let's do 19.2c from the textbook. And we'll get this out of the way and won't have to look at this again. Okay, so this is 19.2c. Okay, so let's see, that states balance the following they balance the following redox reactions. So we have Cr2O7. This is the dichromate ion, and that reacts with C2O4 2-. This is the oxalate ion. Then the products of this reaction are Cr3 2+, sorry, Cr3 plus, then the other one is CO2. And then it says this is an acid solution. Okay, so based on the method of half reactions, you want to figure out what's being oxidized and what's being reduced. So the first step, you want to figure out the charge on each atom in each compound. So note that the net charge in Cr2O7 is -2. In general, the charge on oxygen is equal to 0 in the element, but in the compound, the charge on oxygen is equal to -2. So we can figure the charge on chromium. Okay, so we have 2 times x, where x is the charge on chromium, plus 7 times -2, where -2 is the charge on oxygen. The net charge is equal to -2, so we solve for x. X is equal to, 6. Okay, so note that chromium has a charge of +6. And then let's take a look at, so this has a charge of -2. And let's take a look at this one. So we have the oxalate ion, C2O4 2-. We'll do the same thing. We know the charge on oxygen is -2. We want to figure out the charge on carbon. So we have 2 times x, where x is the charge on carbon, plus 4 times -2. And that's equal to -2. So if we solve for x, that's equal to 3. So the charge on carbon is +3, and that's -2. What's the charge on chromium and chromium 3+? Yeah, 3+. And then what's the charge on carbon and CO2? Okay, we'll do the same thing. The net charge on CO2 is 0, so we have x, where x is the charge on carbon, plus 2 times -2, and that's equal to 0, so we can solve for x. X is equal to 4. Okay, so note that the chromium in dichromium goes from +6 all the way to +3. So is the chromium in Cr2O7 2- being oxidized or reduced? That's being okay, so note that the oxidation number, or the charge, is reducing or getting lower. That means that's being no, the number is getting lower, is being reduced. So that means the chromium is being reduced. So this is the reduction here. Okay, so it's being reduced. Okay, so it's gaining electrons. Okay, so if the charge going from the reactant side to the product side is decreasing, that means it is gaining electrons, which means that it's being reduced. Okay, this is why it's easy just to look it up. Table 19.1. Okay, so in this case here, note that carbon and oxide goes from +3 to +4. That means the carbon is being oxidized because it's losing electrons. So these are oxidized. Now we can figure out each half reaction. So for a reduction half reaction, okay, so the Cr2O7 is being reduced. So we have Cr2O7 2-, and that goes to chromium 3+. Now note that this is not a balanced half reaction. Okay, now note that there's 2 chromiums on the reactant side, only 1 on the product side, so let's put a 2 here. How many electrons are transferred going from Cr2O7 2- to Cr3+? Okay, so how many electrons are transferred going from here to there? One. You have to look at the charge. Because note that from here, one chromium ion has a +6 charge. The one chromium ion here has a +3 charge, but we have two chromates, two Cr2s and Cr2O7. So how many electrons are being transferred here? No, there has to be, because it's an oxidation reduction reaction. It has to be electron transfer. Okay, so if one chromium has a +6 charge, that means two chromiums has 6 times 2 is +12. And we have two chromium 3+ ions here, so +3 times 2 is +6. So it goes from +12 to +6. That means how many electrons are being transferred? 6. So we put 6. We have +6 electrons here. Now note that this equation is still not balanced because we have 7 oxygens on the reactant side, we have 0 on the product side. So one way to balance that in that solution, just add water. So we'll add 7H2O. Now we have 7 oxygens on each side of the equation. Okay, so when we want to balance the oxygen, just add water. But now we've got too many H's. We have 14 H's on the product side. We have none on the reactant side. Since this is an acid solution, acid means H+, so we're going to add 14. So we'll add 14 H pluses on the reactant side. And that balances the H's. So is the conservation of mass law obeyed in this half reaction? Yeah. So it is. Is the concentration of charge law obeyed in this half reaction? Okay, so let's see. We have +14 -2. We have 6 electrons. So that's -6. Then here we have +3 times 2 is +6. So is the charge the same on each side of the equation? Yeah. So this is a balanced reduction half reaction. And just to make sure, is this reduction to half reaction shown in table 19.1? Rolando.
I was reading this article. They were talking about how they're studying the relationship between students and retention versus retrieval, because you can get on a smartphone or the computer and retrieve vast amounts of reference and data, so that you don't have to store all that in your brain. And I was just watching the news the other day. They were showing something about these glasses that you can wear, and they pull up. It's a heads-up display, so they pull up anything from the internet that you want. You just have to.
Yeah, isn't Google design developing something like that?
And IBM actually, or I think it's IBM, is developing a way of through fMRI being able to visualize what you think. So if they can kind of do it with letters now. So you can, if you're thinking of an A, they can actually display an A on a computer just by fMRI, I think it is, and electrodes that they use to.
Yeah, fMRI is functional magnetic resonance imaging.
Right, and so that if you couple those three things together, in the future you might just be able to think something and retrieve what you want for your information instead of having to even type it. So,
yeah, that'd be a good thing. So really, I mean, for me on a quiz and exam, what's the point of giving you questions where you remember, where you're spitting back something at you? You know, memorize this to find that. Because like you can just look it up. But really, what I'm hoping that you learn from this class is how to use, what equation to use in what situation, what do these numbers mean, how to use those numbers. Because really that's what you're going to use when you're a scientist and engineer or health professional. So what do those numbers mean? So with your doctor, your doctor orders a blood test to get all these numbers back. So what do those numbers mean? And if rather amazing, what are you supposed to do? Or if you're an engineer, you're like in physics Olympics, I'm not sure how many calculations you did when you designed your bridge, but they do engineers do those calculations to design a bridge to make sure that it supports a load, and in certain weather conditions. Have you seen that video of that bridge in Washington which blew over?